Okay, we're going to introduce Curt Storlazzi from the USGS. Curt, I hope you're here and you can see us and hear us. Curt, could you tell us a little bit about your background?
Yes, so I I started out as a geologist at the University of Delaware. I migrated west to the University of California at Santa Cruz, where I got my PhD working in coastal geology and oceanography. Um, for a while there, I worked for the PISCO Consortium, which was the Partnership for Interdisciplinary Studies of Coastal Oceans, doing nearshore oceanography as related to biological processes. And moving into the USGS, I started work on the Coral Reef Project, which is looking at the health and sustainability of US coral reefs. And I've worked on that for the past 20 years. I've moved into looking at coral reef hydrodynamics, have then translated a lot of that into coastal hazards around coral reef lined coasts, which is what you'll see the presentation on today.
Okay, yes, so you'll be speaking about wave spectra over the coral flats, as you mentioned, and tell us a little bit more about how you've been specifically involved in that program.
Well, so it originally we were looking a lot at land-based pollution on coral reefs. So we were looking at sediment, nutrients, and contaminants, nearshore circulation. Obviously, a part of that is looking at wave-driven flows across reefs. Kind of hard not to see when a big storm comes by. You get a lot of run-up and flooding, and so that kind of pivoted some of our research into looking at coastal flooding on coral reef line coasts, and we started just looking at, gosh, you see, because these reef flats are very shallow, you've got depth limited situations. The kind of comparing and contrasting low tides to high tides makes you start thinking about the impacts of sea level rise. And so through that, we started a number of projects with managers in the Park Service and Fish and Wildlife and Department of Defense. And most recently, we did a very large project with the Department of Defense, which I'll be showing about today, trying to understand wave-driven flooding on coral reef line coasts and how that may change with sea level rise and climate change and the impacts to things like infrastructure, freshwater availability, agriculture, habitats for threatened and endangered species. So I now run those efforts looking at those hazards in the tropics for the USGS Coastal Marine Program.
Okay, thanks. And before we begin, just why don't you tell the audience one fun fact about yourself that most people might not know?
I, instead of being a coastal geologist and oceanographer, was almost going to study nuclear engineering and go through the Marine Corps option to the the Naval Academy, which would have ended up in a much different situation than I am now. So interesting decisions that get made long time ago and stuff in different places and different experiences. So
Awesome. And actually, a fun fact that I remember about you, and I'm not sure if you remember, but oh boy, more than 10 years ago, maybe 2008-ish or so, you came and gave a presentation at a workshop I was running in Monterey. And I think you were speaking about wave measurements off of Santa Cruz. And it was a great presentation. The only question was someone at the back of the room that asked you where the best surf break was based on your research. So I thought that was a fun thing, and I still remember that one.
oh yeah. That was AWAC measurements.
Yeah, exactly.
Correct.
Okay, so the format we're going to do now is that I'm going to give about 15-minute presentation about how RBR does the wave measurements in terms of the products, the signal processing, some guidance for how to configure it. And then we're going to move in and Curt will give his presentation, which will be about 15 or 20 minutes. And then we'll do a combined question and answer at the end. So I think we'll just move right into it now. So wave measurements, yes, they're not as easy as just making a temperature or a conductivity measurement. Wave measurements are really a statistical representation of what is a complex wave field. And actually, the word significant wave height is a term that Walter Munk defined to try to express the height that would be estimated by a trained observer at sea. So if someone was looking out at the waves, of course, there always are small waves and there always are the largest waves, but significant wave height is what a trained observer would try to define. So that's now taking centuries of observed wave heights and trying to make them parallel to pressure-based and mathematical representations of waves. So RBR makes a lot of different sensors and gauges and loggers to measure waves. They really are all the same. They all have the same, they almost all have the same pressure sensor. They almost all use exactly the same signal processing. Most of the difference is the form factor, how many batteries are in it, and what else you're measuring. So a lot of people will be familiar with the RBR Solo D Wave 16, and we also have all of these iterations as a Tide 16 mode. You'll be probably familiar with our standard loggers, which would be the Virtuoso D Wave or the Duo TD Wave. And all of our CTDs can be configured in wave mode. So as long as you're sampling fast enough in the burst mode, you can make wave measurements. The one that's a little bit different is the RBR Quartz Q Wave 16. The RBR Quartz Q uses a Peros digiquartz pressure sensor instead of the standard pressure sensor we use. The Peros sensor gives two things. One is very high stability, and that would be used for long-term measurements of water level. And the other is that it has a little bit higher resolution. Instead of, it has a little bit higher resolution. So that means not so much for wave measurements, but for water level measurements, you can resolve a little bit better, very small fluctuations in water level. Okay, so those are the different products, but as I said, they're all doing the wave measurements in essentially the same way. They're all taking a burst of pressure data, and then they're doing some statistics to give you out the wave parameters. So ocean waves, yeah, this was the first pressure recording of waves that I ever made, which was about 15 years ago. Now it was deployed in Florida, and it's very shallow, and these are small waves. What we see here is an 8.5 minute record in time. But what's important to notice is that waves are complex. You can get some small waves, you can get some big waves, you can get some sections in time with different types of wave parameters. And so it's important to know that waves are a statistical representation. It's not as easy as just measuring temperature or conductivity, as I mentioned. Here are a couple 8.5 minute time series of waves, and you can see that in this first one here, you can see that the waves are pretty regular for a while, and then you get a little bit of swell that comes through. Maybe it was a ship passing from far away. In the second burst, you can see the waves are very groupy. They have a group period of about 1 minute, and I think surfers know this well, that sometimes you get some nice groups coming in, and then sometimes it's quite calm. And then the last one, you can see the waves really change. In the first several minutes, the wave pattern is more similar, and in the last couple minutes, the wave pattern is more similar, but it's just to represent that waves are quite complex and always changing in time. The third one here to show is what ship wakes look like. This was collected in a river where the water level was around 3¼ meters and very small waves, and then a huge freighter went by, and we got a wave trough that was nearly 3/4 meter, and then lots of interesting secondary motions afterwards. So we'll talk a little bit about ship waves at the end. But let's talk about wave properties. So the most common wave properties that you're trying to measure would be significant wave height, and that's often written as HS, sometimes H1/3 or HM0, and I'll speak about that a little bit more. 1/10 wave height, maximum wave height, and average wave height. And then for every wave height representation, there is a correlating wave period. So for the significant wave height, there would be a significant wave period. For the 1/10 largest waves, there would be a 1/10 wave period. We can give you the wave period for the maximum wave and the wave period for the average waves. The other variables that RBR presents and most people are looking at will be wave energy, which is in joules per meter squared, and the tidal slope. So that's how the water level is changing over the burst duration, and that's usually represented in change of meters per hour. So the way that people calculate wave height is, of course, we measure a time series of pressure, and then from that time series of pressure, we can do two things. The first method would be called a time domain or a zero upcrossing calculation. And here what we do is we remove the mean of the burst, so the mean is centered on 0. And then every time the wave crosses up through 0, we say it's the beginning of a wave. And then when it crosses up through 0 again, we call it the end of the wave. So in this little example, we have defined one wave here. We've defined a second wave here, crosses up again, and then we have the third wave here. And you can see there are little fluctuations within that wavelength, but that's how zero upcrossing defines it. So we can see for this middle wave that's defined, it has a height from peak to trough, and it has a wave length or a wave period from the beginning of the upcrossing to the end of the upcrossing. So we do that, and then what we do for significant wave height is we stack all of those waves from smallest to largest, and we calculate the average of the 1/3 largest waves in that record. And that is significant wave height, also known as H1/3 from the time domain method. And that's what RBR does. There's another way of doing it, which is using the frequency domain. Here we take the full time series of data from the burst, we calculate an energy spectra, as you've seen many times, and then another representation of significant wave height is 4 times the square root of the area under this curve. And that is known as HM0, and it's another similar and very common representation of significant wave height. We pulled up this figure that was published a little while ago in a book called Waves in Oceanographic and Coastal Waters. And what it shows here is a representation of H1/3 compared to HM0. And you can see they're generally quite close, but there's roughly a 7% difference where H1/3 is a little bit lower than HM0 on average. And it depends, of course, in whether you're measuring waves in the ocean, how regular they are versus coastal areas. But you should know that there are some differences, and RBR uses the time domain method, which is H1/3. So we can look a little bit at some data here. This is one burst of wave measurements that we made, and it's measured, we've measured 8,192 samples at 16 hertz, which is gives us a record length of about 8.5 minutes. So from start to end here is 8.5 minutes. You'll see that the pressure is showing at roughly about 18 meters, and that includes about 10 meters of atmospheric pressure on it, so that this was actually deployed in about 8 meters of water depth. And you'll see two things. One, you'll see that there's clearly some waves, but two, you can also see that the tide was going down. So the water level was decreasing over that time period, and it actually decreased about 10 centimeters in the 8.5 minutes. So that would be considered the tidal slope. So this is what the raw data looks like, and you can view it in Ruskin. And then what we do is we remove the trend. So we've removed the tidal slope, and we've removed the mean. And so now you can see that the measurements are all centered on 0. And this is when we would go through and do the 0 upcrossing. So the next steps in doing the wave processing is determine each wave through the 0 upcrossing mode, order the waves from smallest to largest, and then calculate the statistics. Where significant wave height is the average of the 1/3 largest waves. H110 is the average of the 1/10 largest waves. H max, or maximum wave height, is simply the largest wave that's measured. And so this is what Ruskin looks like when it finishes doing all the wave processing. You get a nice display. You get to see all of the parameters. And then, of course, in Ruskin, you can toggle to turn on or off each parameter as you want to see it. And we're going to zoom in just on the parameters here because I know they're small in that first display. So you can see we're outputting wave energy, average wave period, average wave height, maximum wave period, maximum wave height, 1/10 wave period, 1/10 wave height, significant wave period, significant wave height, and the tidal slope. So those are all the parameters that we spoke about, and that's how Ruskin displays it. Let's look a little bit about some sampling considerations. So when you're deploying these in different environments, you want to consider what your sample rate should be, what your burst duration, so how long each burst should be, and your burst interval, which is how frequently you repeat those wave bursts. So let's look at sample rate a little bit. And sample rate is quite tied into the deployment depth that you put the pressure gauge, because the pressure signal is attenuated quite rapidly with depth. So here's a little schematic where you can see the pressure signal is quite large into the surface, but as you go down into depth, the pressure signal becomes attenuated quite quickly. It's particularly attenuated for high frequency waves. So short waves, the pressure sensor is attenuated very quickly with depth. That means, in general, you want to deploy your pressure sensors in as shallow water as possible. Clearly, you can't always choose that, but the more shallow the water is, the higher frequency waves you'll be able to resolve. It also means as you deploy in deeper water, you don't really need to sample very quickly. We'll talk about that a little bit towards the end, where we show you how the Ruskin software will tell you what the frequency limit or the period limit is based on the estimated water depth. But just know that you don't necessarily have to sample fast if you're going into deeper water. The next thing that comes on with sample rate is really the fastest wave that you want to resolve, and you have to keep in mind the Nyquist frequency here. So the Nyquist frequency essentially says that you have to sample as fast as the shortest wave you want to resolve. Sorry, you want to sample twice as fast as the shortest wave you want to resolve. So that means if you sample at 1 hertz, the fastest wave you can resolve is a 2-second wave, or half a hertz. If you sample at 2 hertz, you can resolve a 1-second wave, or 1 hertz. If you start sampling faster, say 4 hertz, you can start to resolve shorter waves, so a 1/2 second or 2 hertz wave. In general, because of attenuation of pressure, if you're deeper than 3 meters, you don't really need to sample faster than 1 hertz because the pressure signal is going to attenuate those short waves anyway. But there's no downside in sampling faster, especially if you have the memory to support it, because you can then start to look at if there's any other higher frequency motions. Okay, the next thing that a lot of people wonder about is burst duration. You can set the system up to sample in bursts in powers of 2, so that's typically 1024 measurements, 2048, 4096, and so on. That, when you relate it with the sample rate of 2 hertz, 4 hertz, 8 hertz, 16 hertz, gives you the burst duration. And typically the burst duration is between 8.5 minutes and 34 minutes. And we'll talk about that in a moment. But what's important to figure out is how long do you need to sample to get a good representation of the wave height? And I like to use an example of watching people walk by the bus stop or the corner, or counting the average height of people in line. And you can understand this because if you want to come up with the average height of a person, you could just measure 1 person and you would get a height, but you know that doesn't give you good statistical representation. So you could measure 2 people, and now you're getting a little bit better of what an average height of people are. But we know that the more people that we measure over, the more statistically significant the average height of the person would be. And that's the same for waves. So we want to measure enough waves that we think the wave field is statistically well sampled. And so the best way to consider well sampled is that you want to measure roughly 100 wave cycles per burst, and you have to then define which wave period you're most interested in, because in every wave condition you will see some very small, very short waves and maybe some longer, lower frequency waves. So you have to think a little bit about what wave period is most important for your study, and then you want to try to set up your burst duration so that you sample about 100 of those wave cycles. So for example, if you're really interested in a 10-second wave period, then you want your sampling to be at least 17 minutes long. And if you do 10 second in your wave period times 100 samples, that means you want to sample for about 1,000 seconds, which is about 17 minutes. If your wave period that's interest is shorter, say you're only interested in 4 or 5 second waves, then you can sample a shorter period of time. 5 second waves times 100 samples is 500 seconds, which, as you know, is less than 10 minutes. So you can run for shorter wave durations. This table here gives you the wave burst duration as a function of number of samples in the burst and sample rate. And of course, you can calculate this quite easily. And the general thing that I see is people setting their systems up for sampling bursts of about 8.5 minutes to 17 minutes. That's kind of the most common settings that we see. If you sample for a much shorter period of time, you're not going to get very good wave statistics for sort of the middle and most common wave bands. And sampling longer is possible, but it doesn't always buy you that much, unless you're trying to measure swell. And Curt probably can tell us a lot about the Pacific swells, because those are the good surfing ones. And they have periods more than 20 seconds, sometimes maybe even 30 seconds. And if you're sampling the swell and you really want to characterize that well, then you should sample for longer durations. The very last thing to speak about is burst interval. So this is how frequently we repeat the wave bursts. And again, this is going to be a combination of your battery and your memory and your deployment duration. But generally, in the open ocean, when we think that waves are going to be pretty consistent from minute to minute and even hour to hour, sampling the waves every 1 to 3 hours is probably frequent enough. In an enclosed bay where maybe you have some different wind and current and wind against current interactions, or things change a little bit faster, you might want to sample a little bit more frequently. But again, this really depends on the battery, the memory, and your deployment duration. Let's move towards the end here in configuring Ruskin. So this is how you can use Ruskin to set the system up for the wave or tide measurements. We have two modes here. One is called Tide 16. And what Tide 16 will do is it's really used for low frequency, such as water level and tide measurements. It will filter out all of the high frequency noise. So when you set up the Tide 16 mode, you choose a sample rate, so say 16 hertz. You choose a burst duration, so say in this case 1 minute, and then interval, so in this case it's 5 minutes. So that means every 5 minutes the system will turn on, it will sample at 16 hertz for 1 minute. And then what the Ruskin software does is it throws out all of this high frequency information. It's not logged, you don't get to keep it later, and it will average it to 1 point. And that point, the time period is set at the beginning of the wave burst. So you'll see this example here. It turns on for a minute, samples for 1 minute, turns off. 5 minutes later, it samples again. 5 minutes later, it samples again. And the data are averaged, and you only keep that one. And what you get here is you get a really nice tidal elevation time series with all of the high frequency waves filtered out. It's important to realize, though, that you don't get to keep the raw burst data. And that's where wave 16 is a little bit different. So wave 16, wave mode, you still set your sample rate, you set the number of samples, and these are powers of 2, as we said, 20, 48, 40, 96, and so forth, and you set the interval. Now, there are two other things that you set here. One is that you set the instrument altitude. This is the approximate distance off the bottom that the pressure logger is going to be deployed. So if you build a bottom frame and you deploy the logger 10 centimeters off the bottom, you would put in 10 centimeters there. And that's used in part of the linear wave theory calculation, the distance between the logger and the bottom. The other part that you set is the mean water depth. And this is simply to help you evaluate what wave periods you'll be able to see because of attenuation of pressure. So for example, and we're going to go through this a little bit more in the next couple of slides, but for example, if you're deployed in 10 meters of water, the shortest wave period you can see is about 5.3 seconds, and that's because of attenuation with pressure. So in this case, it's set up for 16 hertz, 32,768 measurements, which is a 34-minute wave burst, and it's doing that every 1 hour. So you can see it turns on at the top of the hour, it samples for 34 minutes, and you keep all that raw data, you get access to it. Ruskin uses it for the wave processing, but then you also can look at it in Ruskin, or you can export it to MATLAB or whatever you wish to see the details there. So this is height above bottom, estimated water depth, and the estimated water depth, as I said, controls what the wave period is. So these are sort of a feedback loop. So I've got 4 examples here. The first one is if you deploy it in 2 meters of water, you can see that the shortest wave you can see is 2 seconds. So this is covering almost all of the real energy in an aquatic environment, and you'll get some really nice measurements. If you say that you're going to deploy in 5 meters of water, now we're starting to lose waves shorter than 3 or 3.5 seconds. Probably still okay, but the really high frequency wind chop will be starting to be attenuated. If you're in 10 meters of water, as we said, it's about 5.3 seconds. So now in a lot of enclosed areas, a lot of enclosed bays, there's going to be a decent amount of wave energy that's shorter than 5 seconds, and you just won't be able to see much of that. And if you move down to 20 meters, if you deploy in 20 meters, the cutoff frequency or cutoff period is about 7.5 seconds. Still totally fine if you're trying to measure oceanic waves. The swell period in the Atlantic is closer to 10 seconds and longer, and the Pacific even longer, so you would see all of that well. But in 20 meters of water, you'd miss a lot of the high frequency wind waves. Okay, the last slide here for me is just a little bit of a thought for measuring ship waves are what people think of as transient waves. So you can see a nice example here where the instrument was deployed in about 3 or 4 meters of water, and you see the normal high frequency wind waves, and at the very end, a large ship came through, and you get this really big signal that's much, much larger than the waves itself, and has a really nice signature to it. So ship waves or transient waves don't behave with linear wave theory, so you can't use the same zero crossing or frequency domain measurements. You really can't use standard wave metrics. You really have to do your own processing and create a plot like this, and then decide what is the maximum wave height. And then, because of course the period is going to change as the long waves come before the short waves, and it's a little bit more on your own processing. The other thing about measuring transient waves is that I wouldn't suggest you try to do it in burst mode, because if you never know when the ship's going to cross, of course. And if you go and sample for 30 minutes every 1 hour, well, you might be missing half the ship waves. So typically people trying to make transient wave measurements will sample continuously, and they might sample at a little bit slower rate, so they have more memory. But if you're trying to do transient wave studies, I would suggest not doing it in burst mode and trying to do it as a continuous measurement. I said it was the last slide, but I'm wrong. I wanted to put up a couple of resources that you can use to click on and download, and this presentation will also go as a PDF, so these will be hyperlinked. You don't need to write these down. But on the RBR website, we have a nice wave overview that you can read. We have a short section that says, how does Ruskin process the tide and wave data? And we have a little section that says, what's the difference between tide mode and wave mode in Ruskin? And finally, I want to link you to some MATLAB tools that we have. They're free to download. It's called RSK tools. We did give a webinar about this a couple weeks ago, so that's also on our website. But we provide more signal processing in RSK tools, including some spectral calculations. And I think Curt's going to give some nice presentations about wave energy spectra, and I just want to let you know that RSK tools will provide that kind of calculations for you. Finally, I want to remind people about the upcoming webinar. So next week, Greg Johnson will be speaking about CTD and sensor calibrations. And then starting after that, as I mentioned, we're moving into webinar 2.0, which is we're sharing customer experiences. We're inviting you, if you want to participate and use this platform to speak to usually over 100 scientists from all over the world, then get in touch with us. As I mentioned, we already have some good speakers coming in July from Hui and Dalhousie University, and we want you to be part of that. So I'm going to stop, and I'm going to hand this over to Curt, and we'll do questions at the end. Okay, Curt, I think you should be all set to share your screen. Excellent. Okay, please take it away, Curt.
Okay, hold on a sec. My screen's blank. Okay, there we go. So today I'm going to talk about application of field measurements to understand spectral wave transformation across coral reef flats. This is done with my colleagues, Olivia Cheriton, who's probably one of the best oceanographers in the U.S. Geological Survey, and Curt Rosenberger, another good oceanographer and kind of lead on our instruments, mounts, programming, data processing, design. So the background of this work is that on high tropical islands, most of the population, infrastructure, and critical habitats are situated at very low elevations protected by coral reefs. Here you see Pago Pago, the capital of American Samoa, Hagåtña, capital of Guam, Honolulu, capital of Hawaii. You see those big reef flats offshore, causing most of the waves to break in very tranquil waters at the shoreline. On atoll islands, all of the population, infrastructure, and critical habitats are situated at very low elevations, again, protected by coral reefs. The picture of Ebi there, that little strip of land has 30,000 people on it. The lower pictures there show normal houses, the critical infrastructure, and the airport there, just extremely low situated. Actually, if you see the airport there, I don't know if you can see my cursor, but the stains on the runway on the right side of it are from seawater washing over onto the runway, and that's the main air link out of the entire atoll, which is the capital of the Republic of the Marshall Islands. Now, the Department of Defense is really interested in this is because a lot of their assets across the Pacific and are, again, coastal and thus protected by fringing coral reefs. So you've got wake, kwajalein, multiple spots on Oahu, both protecting Hickam, Pearl Harbor, and MCAS Kaneohe. So one of the big problems is that sea level in the Pacific Ocean has been increasing around rate about 2 to 3 times the global average, resulting in to a third of a meter of net rise since 1990. This has been related to changing wind patterns, but this is on top of the increasing global average. And we know the National Climate Assessment, IPCC reports, others provide global sea level rise projections that range from 0.2 to 2.0 meters by 2100. There's large regional variability. Actually, the tropics, the water levels will be higher due to melting at the ice caps and gravitational attraction issues. But one of the biggest things they talk about, even those scenarios, is the collapse of those ice sheets. And if you read Science and Nature, we know that those ice sheets are ungrounding, and thus we're looking more at the higher end scenarios than we're looking at the lower end scenarios in terms of probability of sea levels at the end of the century. So historically, large waves have flooded islands. You know, every 20 or 30 years, you'll get a big tropical cyclone, a large, really large, high latitude anticyclonic frontal system will come through and throw big waves down. And, you know, they could damage infrastructure, ruin freshwater supplies by saltwater contamination, and destroy agriculture. The problem is with that third of a meter sea level rise, and most of these coastal areas being very low lying, now wave-driven overwash events are happening multiple times a decade. And what this means is sea level rise will continue to exacerbate those wave-driven flood hazards and on US and the US affiliated islands, which is the focus of our work. So the objective of this research has been to provide some basic understanding that we can extrapolate globally, but also specific information for specific sites on storm ocean surface wave-induced flooding and overwash of coral reef islands. And this is showing a picture of the north side of Roynamore Island on Kwajalein Atoll. This is a large overwash event that we actually measured. This is funded by the U.S. Department of Defense Strategic Environmental Research and Development Program. So the idea is trying to understand the processes, the wave processes leading to these overwash events, and how that will be impacted by sea level rise. So here we see a map view of our instrument deployments. The N0, and then below that you see cross sections, the upper cross sections, the one on the west, the lower cross sections, the one on the east. And the N0 out at the reef edge, or the edge of the reef at about 23 meters was a Nortec AWAC. If you see off to the edge of that picture at about 28 meters, the atoll drops off at about a 85 degree slope to about 2.5 kilometers water depth. Incredible topography or morphology there. The N1, N2, N3, N4 instruments were rbr virtuoso D-wave gauges that were how they were deployed. Well, first, I'm sorry, the AWACS were deployed via lift bags into these environments. And one of the funny things about it is when you travel 18 hours on a plane, you can't guarantee, and you have to plan around a Department of Defense operations. You don't always get to pick your weather conditions. And so here shows our 45-foot boat heeling like 20 degrees in about a 3-meter swell for deployment conditions, which is not always super fun. The like I said, the rbr virtuosos bolted on the upper fore reef and the reef flats. We basically drilled in stainless steel rod and threaded these brackets that held the Virtuoso wave tide gauges firmly onto the reef flat, because in many places, as you see here, there's just nowhere to deploy it with weights, with the pressure sensors down, anti-fouling, things like that. As you see, the reef flat at low tide gets dry even all the way out to the reef crest, which makes pretty fun conditions for deploying and recovering such instruments. So how we set up, going back to Eric's presentation, every hour we collected pressure measurements at 2 Hertz in 34-minute bursts. We had atmospheric pressure measurements from an airport weather station. We were subtracted from each pressure burst to get sea pressure values to convert to water levels. We did not use the onboard processing for a reason I'll explain in a second, but so we were computing the one-dimensional energy spectra using Welch's average modified protogram, which has a Hamming window, 50% overlap, and the pressure response factor was corrected, was applied to the spectra. The reason why we had to go with the, we did not go with onboard processing is because we wanted to look at the energy in different frequency bands. So we looked at incident, which is kind of like your up to 25-second waves, infragravity, which is 25 seconds to 250 seconds, and then very low frequency, which is greater than 250-second waves. Now, as Eric was talking about trying to measure the 100 waves and to get variability each hour, we were not obviously catching 100 VLF waves or infragravity waves using our sampling method. Then we computed the significant RMS wave heights, were computed via the energy spectra for each frequency band, and the peak wave period within that frequency band was the frequency of the peak energy, and the total energy was computed via HRMS. Okay, to show you some data and some cool things about wave transfer and ratio across reefs. So the plot on the right is showing from the offshore across the forereef to the outer reef flat, the inner reef. So if we think about offshore, would be on the schematic on the left, would be down on the blue, like the greenish area below that forereef. The forereef, the second row of the plot on the right. So it's the purple. You see the relatively narrow banded incident band or swell coming in, and the wave breaking occurs between the forereef and the outer reef flat at the reef crest. So by the time we get to the outer reef flat, which is now our middle row, you see the energy spectra has decreased significantly. A lot of wave energy has been dissipated by breaking at the reef crest. But what you start to see is more and more energy on the left sides of the plots, as energy is slowly being pumped into lower frequencies. By the time we get to the mid-reef flat, the energy in the infragravity band is at the same level as in the incident band. And by the time we get to the inner reef flat by the shoreline, the incident band wave energy is actually much smaller, and the waves on the inner reef flat are primarily dominated by infragravity and very low frequency wave motion. So that wave breaking at the reef crest, because as Eric was talking about, there's wave groups. So you've got a group with bigger waves in a depth limited situation. They break slightly further offshore. The smaller waves in the other part of the wave group break a little closer to shore. So you have a moving break point. That moving break point pumps things at wave group frequencies. That energy, that break point forcing, forces this energy into these lower and lower frequencies. And you can kind of see this picture here on my colleague. So you have out here in this picture, it's about 8-second waves, and out in the open ocean where it's blue. And as you move down to the bottom of the picture, you see kind of like a packet of like 3 or 4 waves. And it's kind of flat, and then a packet of 3 or 4 waves where there's a little wave breaking. And so these are these infragravity waves with incident bands, smaller incident band waves riding on top of it. So to show this more in an individual burst, we're showing this now from, again, the forereef, from the outer reef flat to the mid reef flat to the inner reef flat. And so you see, again, on the forereef and outer reef flat, you've got these waves and this incident band. They're, you know, these very short periods. By the time you get, and as you move down the plot, down to the mid-reef, you see all of a sudden you're starting to lose a lot of those high frequency, those incident band waves, and you're seeing them being dominated by longer period motions. The red is now kind of your infragravity on these lower ones, or sorry, it's actually just a moving average, but you see that moving average, which is kind of showing what like an incident band or the infragravity band, is getting larger relative to the incident band periods. And as you get to the inner reef flat, you actually see that these waves get very, they're no longer sinusoidal. And if we actually track these dotted lines where we're tracking these three big wave groups onshore, you see as they move onshore, again, we're losing those sea swell band waves, pumping more and more energy into these lower frequency waves. And they're getting very both asymmetrical and skewed. So in terms of asymmetrical, that means they're pitched onshore, and negative asymmetry is increasingly pitched onshore, and skewness is they're becoming much more pointed. And so you can see this asymmetry and skewness values there. And so they're basically become almost like a nonlinear bore-like feature. And you see that in this bottom picture on the right, where they're breaking at the reef crest, the bores, as you move from left to right across the photograph, all of a sudden, kind of by the left or the right side of the photograph, you actually see one of these infragravity bore packets with the high frequency incident band waves riding on top of it, because in this depth limit situation, that infragravity waves provides additional depth for those incident band waves. And again, that's what we see on the time series, the subplot D, is you see these infragravity bores with larger high frequency incident band waves on top of it. When you get to the bore troughs, it's a depth limit situation, so you don't really see those incident band waves. So why do we do all of this? Well, A, to understand wave processes, but also to calibrate models to do forward projections. And so all of these, that we used all this data, don't worry about all the numbers in the plot, but basically we used all of our wave tide data, these are the different columns, to look at water levels, mean water levels, so that's our tidal levels, our setup, so the water levels above those tidal levels, and our basically our incident band and infragravity band waves at those different locations. And then we can compare it to a model to calibrate and validate the model. And this is really important because most of these models, in this case we're using X Beach, was developed for linear, low gradient sandy shorelines with very low slopes. Well, our situation violates most all those assumptions. So we had to heavily modify, Deltares heavily modified the model, what we call X Beach non-hydrostatic plus, to basically take in these high slopes and things like that. But one of the things we realized in this with the model to get the data to fit the model well is that we had to have spatially varying hydrodynamic roughness of more than 2 orders of magnitude larger than for sandy shorelines. And that's the presence of these very rugose corals in certain areas that cause high hydrodynamic roughness. The other thing is breaker formulations are usually, somewhere around 1, but because of these really steep slopes here, our formulation was much lower than that. So some of these things that the data, not only did we learn about wave transformation processes, but the physics we have to incorporate in the models to get them to work accurately. So what that did then is allow us to model waves with sea level rise and to be able to basically do these kind of simulations where now all of a sudden we can look at wave-driven flooding of these islands, how it's going to impact infrastructure, freshwater availability, and things like that, which was the ultimate goal of this project, is to look at this sustainability and future habitability of these islands. But we needed these tide and wave information to calibrate and validate the models, because if we can't show that the models work accurately now, it's useless to try to do forward simulations. So the nice thing then, what we can do with models is that we can take that model data, run tens of thousands of simulations to see how things like what we're looking at are these plots are on the y-axis or run up, and see how that is a function of different parameters such as H is water level, or I is wave height, J is wave steepness, K is roughness, and how we can look at how those different wave parameters that we looked at, or wave and water level parameters, tide, setup, which are the different colors, very low frequency, infragravity, sea swell bands. And so those calibrate, the field data allowed us to use the model to better understand wave processes above and beyond what we could actually measure, either in terms of wave heights or water levels or reef widths, like M is reef widths, or different friction coefficients in K, like if you have a really healthy reef versus a really degraded reef. So it's allowed us to really understand the wave processes, the inherent geologic controls, the reef controls on those wave processes, and then how all of that may be modified by sea level rise and climate change. So that's all.
Okay, Curt, thanks very much. It's always interesting, and to have some nice photos and graphs go along with it makes it really nice. I'm going to open this up for some questions. We had a number of questions that were asked, and some of them were addressed in the first section. People, I think, were very focused on your presentation, your plot, so they weren't banging in questions, but we typically get questions afterwards. So I'm going to open it up for anyone that wants to pop in to ask questions with their mic, or if they want to text them into the chat group, I'll read them out loud, and then Curt or I can try to answer them.
I have a question, Eric. Is Carol Jansen in Alaska?
Hi, Carol. Welcome. Please go ahead.
Yeah, getting my wave education today. Thank you. It was a great, great seminar. Interesting talk on the run-up. I'm sharing that with, we're up in Alaska. We have storm surge run-up problems here as well with low-lying Western Alaska villages and whatnot. So one question is, will this video be available for viewing after today?
Yes, we are recording it, and we're recording the questions as well because people like to hear them. And then I'll work with Curt to figure out which portion of his both video and PowerPoint we'll be able to share. But
okay.
But check back on the website, which is normal rbr-global.com. Go to webinars, and you'll find recorded video and PDF download in the next day or so.
Excellent. And then my only technical question, which will be an easy one for you to answer, is when you are doing your the settings for your wave sampler, the distance off the bottom, how accurate does that need to be?
Yeah, I was worrying someone's going to ask me that when I was putting this together last night. So I personally don't have an exact answer. I'll let Curt weigh in, or maybe anyone else does. I think it does not need to be accurate within the centimeters range. I think it probably is good to be accurate within the tens of centimeters range, but this all feeds into the total accuracy of the system. Unfortunately, I don't know, but I'm positive you don't need to get to the millimeter. Curt, do you have a better sense of that, or maybe anyone else can jump in?
Well, that's just one of the calculations you make, at least for, I mean, you're trying to look at how wave orbital motions and the pressure wave comes down to the seafloor and how that, you know, degrades with depth. I mean, that's the depth measurement, but I think then you're just correcting that depth. So like, hey, you're in 10 meters water depth, but your instrument's 2 meters above the bed, then you're 8 meters below the surface, right? So it's to figure out the pressure response correction, I believe.
Yeah, and again, it probably is related to, and this is just wild ass guess, but related to how deep it is. If you're in very shallow water, it might be more sensitive. If you're in very deep water, it might be less sensitive. So I guess, Carol, the best answer is that in 15 years, no one else has asked me that, so it must not have massive sensitivity.
I think it comes down to also what you're using the measurement for, because like I know for just looking at large scale, low frequency processes, you might just remove the mean of the water depths from the pressure sensor information. You just take that mean out, ignoring waves now. But for tidal measurements, like if you want to actually do tide, you need to survey the sensor in, and that's just an area I'm not an expert in. So anyway, that's a good answer. That's as good an answer as I need. Thank you,
Eric.
Okay. Yes.
Eric, this is Curt Rosenberger.
Hey, Curt. Hey, welcome.
How's it going?
Good, thanks.
I will make one comment on that. what we found was that it is important to get that at least, 50% of what you think it is before you deploy the instrument. My understanding was that at least at present, the way Ruskin is set up, you cannot correct for that in your post-processing, that the wave calculations that Ruskin makes are based on that initial value that you enter when you set up the instrument. So it is actually pretty important to get it right at first. And we have run into issues where we didn't really know exactly where the instrument was because the divers didn't take any measurements. The one example I'm thinking of is in Monterey Bay. We had 3 RBRs on pilings of wharves in the north end of Monterey Bay, and divers put the instruments in, and the water depth was on the order of 8 meters or so. And we didn't have good control of where they were, and we had, I not knowing, made the mistake of not entering a correct value, and we ended up we couldn't use the Ruskin values for wave measurements because we ended up doing the post-processing ourselves anyways. But I would just point out that that is important to get correct. And I don't know, maybe that's something that RBR can change in future versions of Ruskin, that one could go back and change that value to get correct.
Yeah, that's a good point. I think at the moment you're probably right that there's not a way to change that if you entered the wrong thing. So you'd have to do the processing yourself if you found out that what you entered was really far off. And Jana had put a really nice comment in here, which is useful, and I think she's right on, which is saying that in very shallow water, in the order of 10 to 30 centimeters of water, you should have centimeter scale accuracy to correct for the pressure attenuation. And that's similar to what I said to Carol. I think that if you're in shallow water, you need to be more accurate. If you're in deeper water, it's not as accurate.
I'll say one other, sorry, let me just make one other comment that reminds me of something that we do when we are in very shallow water on hard bottom, like the pictures that Curt was showing on Roy Moore. When possible, we actually try to survey our instruments in with GPS, with the post-process corrected GPS measurements to get very high accurate measurements of ellipsoid height of the instruments, so that we know exactly where they are in space, and not just what the water depth, what an average water depth at the site is. And that way it's actually easier to relate all of the measurements from across a reef like that with high rugosity, because then you know exactly where all the instruments are in space to centimeter accuracy. Of course, that only works if you can get a TopCon rod. And like Josh, you saw that one picture of Curt. He said, "There's my colleague out on the reef." That was actually Josh with the GPS rod right on. I mean, he was
in the waves,
had it literally right on top of the RBR. He measured the distance from the top of the instrument to the pressure sensor. I mean, it was, so we got the positions of those instruments within centimeter accuracy.
Cool.
Which is really important for when you're trying to look at setup variations. I'd just like to point that out. And I can't remember who it was talking about like tides. The same thing, if you're going to put a tide, you want to put one in for long time tide measurements, you really have to measure those in very accurately, so that you get where that, basically to get your tidal datum is correct.
There were a couple questions in the chat about the best way to measure infragravity waves, and that's something that I don't have really any experience specifically in. My broad understanding is infragravity waves generally have periods of a couple minutes, but could someone comment a little bit more on that, and if there's a sampling scheme or an analysis tool that is better than sort of the standard linear wave theory? Because I suspect that those aren't considered linear waves in the coastal water.
Well, I can say for us, we initially did that and used linear wave theory to break it out. When you start, especially getting into very non-linear stuff, we are making assumptions with that. But there's, oh gosh, sorry, I'm trying to bring up, Matthias Gowan wrote pulled some data out of for looking at very low frequency waves on reefs. I'm sorry, I'm trying to get what this method is that really works for the Hilbert-Huang transform. That's Hilbert, Hilbert hyphen Huang, Huang transform. So instead of, usually we're basically using a fast Fourier transform. He proposed that the Hilbert-Huang transform is more computationally expensive, but can capture the wave shape more accurately. So to looking at those nonlinear and longer frequency waves, that's a good, the best tool to use, especially if you really want to look at them accurately. And I'll put that into the chat so people have that reference.
Thanks. Sebastian asked a question about the different form factors for the RBR products, why some are smaller, and so they're all really doing the same thing. As I said, they're using the same pressure sensor, except for the Quartz Q, which uses a Peros digiquartz. So the reason is some people prefer smaller with just one battery. Some people prefer larger with some extra batteries. So Curt's he's moved over more recently to the larger form factor, which is the standard loggers that have 8 AA batteries, because they do have more power inside them than the ones with a single battery. It really evolved more in the different RBR products. For example, the standard loggers also have the possibility of doing a conductivity, a CTD measurement, and we don't have that conductivity option for the smaller ones. So that's why most people use the larger ones, and the smaller ones are used just for form factor. But in terms of accuracy and sample rates, it's the same across all of those products. Okay, Chip's giving us some spam. That's fun, Chip. No problem. Okay, open up to other questions, either by normal microphone or in the chat window.
Hi, sorry, this is Alexander Ray. I was just wondering.
Hey, welcome.
Hi, I was wondering if you could elaborate or if there's a process for correcting for atmospheric pressure. Do you have to set a specific atmospheric pressure at the beginning and then the sensor will use that for the whole run? Or can it be adjusted dynamically if there's some cool stuff going on, like hurricanes?
So I'll give you my answer and then someone else can join in for more answer. So in the Ruskin software, you can set the atmospheric pressure. It's just a constant at the moment. So you would and it comes with something set as an average atmospheric pressure already, and then you can fine tune it, but it's just a constant. So to correct for varying atmospheric pressure, such as a hurricane, you would have to do that in your own post-processing using your own time series. There's not a way to do it in Ruskin. You probably know this more than me, Alex, because you're the wave superstar, but my understanding is that for wave measurements burst to burst, atmospheric pressure is going to be pretty constant, I would imagine. So I don't think it changes in terms of statistical wave height measurements if you have a low pressure system going over from burst to burst, but certainly does for water level. But maybe you can let us know more. I think
that oversells my background a little bit. But yeah, for waves, I was thinking more for water level, and especially like very dynamic water level systems where there's a lot happening. For waves, I don't think it would have much of an effect.
Yeah. So you would have to measure the atmospheric pressure. And Felipe asked a question, which is RBR used to sell a vented pressure gauge, which was used for tide mode. It was called TGR 1050 HT, and we haven't sold that for maybe a decade. So you have to use atmospheric pressure that's logged somewhere else with the barometer, or you could buy another RBR Solo D and get the lowest pressure rating, which is 20 meters, and that actually functions as an extremely good barometer in the air.
Oh, cool. Great. Thank you.
Okay. Yeah, thanks for chiming in. Thanks for joining.
Yeah, Curt, Eric, this is Curt Rosenberger again. I'll just say we do that every deployment. Although we often are in an area where an airport is nearby, we always put a pressure sensor on land also, just as a backup for the atmospheric pressure, because that is obviously really important to remove that post-processing. Sorry, I just have one other question about thinking about the low frequencies. It got me thinking about one of your figures talking about the zero upcrossing method, and that Ruskin does a detrending and removes the mean. However, I did notice in your figure there was some low frequency motion in that particular time series that you provided, which showed that some of the waves never cross zero. And I was wondering if you could speak to that. Is that I mean, it literally, the zero up crossing, I haven't used it. So the zero up crossing literally depends on the time series crossing zero. Is that correct?
Yes, and so, which is a function of frequency, because I think the high frequency waves almost all were crossing zero, but for example, there could be a very low frequency wave that wouldn't cross zero. That would be my way of thinking about it quickly.
Well, but what I noticed was that there were some low frequency which dropped to the water level, which made it such that some of the higher frequency waves didn't cross zero.
Yeah, so in that case, that would show up.
They're not getting captured. I mean, I'm sure it doesn't make a huge difference in the system.
Well, I think the amplitude might not be affected by that, but that would shift the average period to something longer, because it would show up as a very long period wave with a pretty small amplitude. That probably would bias that in that respect. But that probably wouldn't; those waves probably wouldn't show up as the in the highest 1/3 or highest 1/10. So I don't think it would affect significant wave height.
Oh, right. That's true. That's true. Yeah.
But so that's why at a lot of times we do this partitioning where we have to use the burst data and partition it ourselves spectrally, because the zero up crossing method won't capture those different frequencies, like a higher frequency riding on a lower frequency.
And I think it's very, very common for people to use Ruskin to do a quick look and try to understand what the general wave environment was, maybe which days or weeks had bigger signals. And then I think lots of people pull it into their own post-processing. I know, for example, I know you do, I think Alex does, and probably everyone else on this call. So it's sort of a good tool to have, but sometimes people bring it into their own post-processing afterwards. Okay, let's see. I've got Chip was texting in here. Cool. The pressure sensors, identical in sensitivity range, or they are very dependent upon the depth of the rating of the instrument? That's a very good question. Accuracy and sensitivity of pressure sensor depends on its depth rating. Yes, okay. So all of the RBR loggers, the compact and standard, have the same type pressure sensors, but every time you order one, you get to define what the pressure range will be. So we offer standard ranges such as 0 to 20 meters, 0 to 30 meters, 0 to 50, 0 to 100, 200, and deeper. And the accuracy is a function of the full scale. So the more accurate sensor, therefore the also higher resolution, is going to be a function of the full scale. So if you're really focused on wave measurements, we would generally suggest you go with a 20 or 50 meter wave pressure sensor. If you're going to be profiling down to 750 meters, you could still use it for waves, but if you're in shallow water, you're going to lose a little bit of accuracy, which I think will just translate into a little bit more noise in the system. But the accuracy and sensitivity are a function of the pressure sensor, and you get to choose that at the time of order. I think that's all that I've addressed all of them so far. Is there anything else? We're happy to join, but also I want to thank Curt and another Curt, and then the other folks that joined in as well. It was a really interesting discussion, and I really appreciate everyone's feedback. And I think as a community, we've got a lot of good answers here.
Thank you, Art.
Okay. Thanks, everyone.
Thank you.
Please join us next week. Look forward to it.